Hello and welcome to another video. In this video we're going to be going over the problems from Weekly Contest 395. And so let's get started. So in this first one you're given two arrays, and basically every element in nums1 has been incremented by some number to get every element in nums2, but they're not necessarily in the right order. So as long as they contain the same integers with the same frequencies, it's correct. But basically, like here in this first example, if you take every single one of these and add 3, then you'll get all these. They'll just won't be in the right order. So we'll just get like 5, 9, 7. But what you can do is you can actually just sort them. So if you sort the first array and you sort the second array, then you can just do the difference of any two elements and figure out like what's the change. So like 2 and 5 means you take the first element and you add 3 to get 5 and so on. But instead of sorting them, we only need one element and we need a matching element. So all we have to do is just get the smallest one of each, and then they have to be the same. So that's all we need to do. So just get the smallest element of each array and then get the difference, and it's always going to be that. So pretty easy. Yeah. And then in the second one, it's kind of the same thing, but like a tougher version. Let me see a drawing of it. I do. Okay. So here, it's kind of similar, except now you're not using every single element in nums1. So it tells you use every element in nums1 except for 2, and then you use every element in nums2. And they basically tell you like there's a bunch of solutions that can happen, but you want to return the minimum possible integer that you can add to all of these to get all of these. So in this first example, you can add -2. That would be the smallest, because if you add -2, you would get 2, 18, 14, 10, 6. And then if we get rid of these two, then we would have exactly what we want. So it's kind of the same thing here. And in the second example, the smallest thing you can add is 2. So you would add 2 to both of these 5s, and then you would do that. So it's kind of the same thing. So you can basically notice, like, let's say I have this first array. You can kind of do the same thing. You can sort it. So 4, 8, 12, 16, 20. And then we can have the second array. And we can sort that as well. So the sorted second array, pretty easy. So it would just be 10, 14, 18. And then basically, there's only a couple solutions you actually have to test after you sort. So because you know that you're deleting 2 elements from this array, if you think about it, these things still have to line up after deleting 2 elements by just adding a number. So for example, let's say I don't use these 2. That means these 3 have to map to these 3 by adding a number. And let's say I don't use like some other 2, maybe these 2. That means these 3 have to map to these 3. And so if you think about it, because you can only delete 2 elements, all you really need is the same kind of thing, is you need the 2 starting numbers. And so if you can only delete 2 numbers from here, that means you're guaranteed that the first starting number will be one of these 3. Right? Because if I delete this one and something else, that means the starting number will be this. If I delete these 2, the starting number will be this. And if I don't delete any of these, then the starting number will just be this. So essentially, no matter how you delete things, the starting number will always be one of these 3. And then that's all you have to do. So you just say, okay, so let's say this is the starting number. If this is the starting number, what's this difference? So the difference is 6. So I'm just going to try a difference of 6 for all of these. And I can only have two numbers that don't line up. And if there's more than 2, that means this doesn't work. So if I try a difference of 6 here, so this will line up, then this will line up, and this will line up. And then these 2 are like, you basically just need one of these numbers to line up with one of these, and you are allowed to have 2 redos from here. So these 3 will line up, and then you'll be done. And then this is fine. So then you need to test other possible starting locations. Like we tried this starting location. Now let's try this starting location. So if this was a starting location, then the difference here would be 2. right? So we can try 2, and we can try this being the starting location. So we'll say this is crossed out. This is one of the ones that's crossed out. Now we'll try it like this. So this is 2, this is 2, and this is 2. So that also works. It's not always going to work, but this does work in this case. And we don't care about the last one, so we'll say like that's crossed out. So now we have 2 solutions. And then finally we'll try this map, right? The first 2 numbers crossed out, and that's the last starting number that we try. So this is -2, so we can try that. So this is -2, -2, -2, and that all worked. So essentially you just need to, you only need to try 3 different starting numbers. Either the first number mapped to this, the second number mapped to this, or the third number mapped to this. Then when you have those, you just run this thing of saying like, okay, I'm going to try to map all of these with 2 numbers crossed out. And it's pretty easy, right? You just need to get all of them to map, and every time there's a mismatch, you just cross that number out and you move on to the next one. So for example, let's say I was trying 6, and this was like, I don't know, 4 or 6, and this was 8. Yeah, so this was 8, and this was, let's say, 12. Then I'd be like, okay, I'm trying to map these 2, so I'm going to try the number 6. So these 2 match, which is good. These 2 don't match, so I'm going to cross this out and now try to match here. These 2 match, and these 2 match. So I have all my matches, and then I'm good. And that's kind of the idea, and sometimes not all of them will match. But essentially, all you need to do is sort both arrays, and then try 3 possible starting maps, this, this, and this. And one of those will always work, and if multiple work, you just pick the smallest one. So let's take a look at the code there. So basically, I have this check function that does that. So this check function will just check the mapping, and I see how many errors I have. And if I have more than 2 mismatches, I just return false. So I make my result infinity, and then I try the first 3 numbers of nums I, or nums 1. So I calculate the difference, I calculate it what it needs to be, and if it succeeds, then I just minimize my result to the smallest of these 3. And that's basically it. So this is like an n log n. But if you actually look at these constraints, the array is pretty small, but the numbers are pretty big. So you don't want to just try every single starting number. It can only be one of 3 after you sort. So you just try only those 3. So this is basically n log n, where this is the length of this array, and this is pretty short. You don't want to try like all these brute force or something, because that would be a lot worse. All right, let's move on to the next one. Get rid of these. The next one should be over here, I believe. Yep. This one is not too bad as well. So basically, you're given a number, and then you're given of how many numbers you need in an array. So you're given like 4, for example, and then you're given how many numbers you need in an array, and that array needs to have consecutive numbers. And all of those numbers in the array ANDed together must equal x. And you're asked to get the smallest possible array where that's true, and then you're asked to return the last value here. And if you actually notice, the constraint n is 10 to the 8th, so we can't actually like build the array. So we can't build the array, so we basically just have to figure out like what number does this have to be. And so the basic things you have to know for ANDing is, for example, if we want 4, so 4 is like this. So in order for the AND of numbers to be 4, every single number has to have a 4 in it. Well, yeah, pretty much. So basically, like this is 4. That means the third bit of every number here, in order for this to be this, has to be 4. So basically, like every other number has to be exactly like this, and then all the other digits of the number have to be different. So hopefully that makes sense. And then they will be ANDed together to be 4. So for example, if we have 4, 5, 6, so let's look at 4, 5, 6. So 4 is this, 5 is this, and 6 is this. So because they all are the same in this digit will stay a 1. Like, for when you AND a bunch of numbers, the only time that 1 stays a 1 is if every single number has that 1 being a 1. And yeah, and then the other stuff can be whatever. So you basically have to recognize that you want the array to start with x because you want every number to have x in it. So that's why you want the array to start with this. And then so these numbers don't have to be consecutive. They just have to be like greater. So you can see like here, they don't have to be consecutive. They just have to be greater. So your first number is going to be 4. And then you basically figure out like what should my next number be? Well, I could have something like this, and then my next number could be like, I don't know, like this. And this will technically work. So if I AND these together, this will technically work, but this will be too big, right? So if I have this and then I have 4, so let's just get rid of this. So if I have these and then I have 4, like this, these ANDed together will actually give you 4. But the problem is this biggest number is now way too big. So you're basically trying to figure out like what are the smallest numbers I can use where them ANDed together will be 4, but the biggest number is the smallest possible. And basically what you can realize is, so like I said, in order to get x, all of the ones in x have to be in every single number. So every single one of these numbers has to have the third one be a 1. But everything else can be whatever you want, as long as they're not all like a 1 as well. So all like every number has to have a 1 as this third one, but everything else can be whatever you want. And so basically you're trying to make these numbers as small as possible, but they have to be bigger than this. So what's the smallest number bigger than this where I can just change one bit? It's just going to be this, right? And then when I AND these together, they will be 4. And then what's the smallest number bigger than this? Well, it's just this. So basically, the kind of idea is you separate your number into 2 sets of bits. 1, bits that must be present in everything. And then you have bits that are optional. So for 4, if we go back, we can even make it an array to make it easier. So for 4, this bit is 1, 0, 0. So this bit has to be a 1 in every single number. But these bits can be whatever we want as long as they're not all 1s in every single number. So because they can be whatever we want, we basically just want to use the smallest numbers possible. And so this is basically kind of like, given x bits, how can I make n numbers where the biggest number is as small as possible? And so that's pretty simple, but I don't really need to care like how many, like how I don't really need to build every single one of them. I only really need to build the last one, right? But essentially, like if we have 3 bits, how do we build like 5 numbers where the 5th is the smallest possible? Well, let's say we start at like 1, then we go to 2, then we go to 3, then we go to 4, and then we go to 5, right? So the 5th number is the smallest possible. So we didn't need to build all these. We can just say like if we want to know what's the 5th what's the whatever biggest number possible to build, like what's the 5th biggest possible number given we have enough bits, like we just have as many bits as we want. Well, we could just figure out, okay, so the smallest number is actually the smallest number is 0, then it would be like 1, 2, 3, 4. So because the 5th number we're trying to build is a 4, all we have to know is like what's the bit sequence for a 4. So the same thing for this n. So let's say we're trying to build like the 151st smallest number we can or something. All we'd have to know is like, okay, so we're going to just build 0 from 150. So what's the bit sequence for 150? And let's just say the bit sequence for 150 happens to be, we'll just make something up. So let's say it's like this: 1, 1, 0, 0, 1, 0, 0. Basically what you have to do, so let's say in fact we started with a 4. Let's say this is our example. So we start with a 4 and we try to build, we try to build like the 150th biggest number starting with a 4. So like I said, the smallest number would be just, and so basically all of these numbers would basically be like 4, 4 plus 1, right? And so on. And then the last number would be 4 plus, if we're trying to build 150, so we'd go 0 to 150. So 0 would be 4, and then the last number would be 4 plus, or let's say we're trying to build the 151st biggest number. So the last number would be 4 plus 150. So basically what we need is we already have the 4-bit in place right here. So we need the rest of this thing to be 150. And that's so actually, sorry, we don't need the rest of this thing to be 150. We need to pretend, we need to, out of all these bits, figure out like what are the 150 numbers we're going to build, and then what's the 150th biggest number that this, so this bit stays the same, but we can change all of these other bits, right? And so basically all you do there is the bit that has to stay a 1 you ignore, and then every other bit you just change to all the bits of this number. So what I mean is, this bit you would change to this bit you would change to this bit you would ignore because this has to be this because this is the one that ensures it's a 4, so we'll leave it like this. Then this bit will line up with this bit, so this will be 1, then this is 0, 0, and then 1, 1. And that's essentially the 150th biggest number you can build starting with a 4, right? Because if we look, like if we start here and we just go number by number, so the smallest number is 4, then we could build 5, then we could build 6, then we could build 7, and so on and so on and so on. So the basic idea is get number that is last, right? And like I said, if n is something, last number will be n minus 1, because you're just going to build 0 to n minus 1. And then you just take all of the bits that you are allowed to change in your current number, in your x. Remember, we're always going to start with x, because we want to start with the smallest number possible. And then we're just going to change we're just going to match every other bit to the bits of the number we're trying to build. So we can look at this example for this as well. So here, n equals 2 and x equals 7. So let's do that one. So for 7, and this will make a lot of sense, hopefully. So 7 is like this. And so if n equals 2, basically, once again, like if we have to have two numbers, we're just going to build 0 and 1, right? So what does 1 look like? 1 just looks like this. So all we need is the first available bit to just turn into a 1, and then we have what we need. So all we do is the first available bit is here. We just turn that into a 1. Everything else matches. And what's this number? It's 15. So that's going to be our last number. So for example, if this wasn't like, if n wasn't 2, if n was like 10, for example, so 10 would look like this, then we need these bits that are available to line up like this, because these are the only ones we can change. These have to be the same. So we just have to increment these one at a time, right? So basically you can think of like all the available bits as one whole new number, and they have to match up the number you're building. So if you want 10, if you want like the 10 would technically be the 11th biggest number because it would be 0 to 10, then you would just make the number like this. This would give you the 11th biggest number where everything is a 7. So whatever this is, that's basically it. So you just have two sets of bits that have to stay the same to actually make the and of every single number this, and then everything else just alternates, and you just keep increasing and increasing by 1. So you don't actually need to increase by 1. You just need to figure out, like, is this bit taken? If the bit is taken, leave it. And if the bit is available, check what bit am I currently on in my number. So what this will actually look like in my code, just to give you a brief overview, is, so I'm going to check. I'm going to have like an index of every bit. So let's say we start here. And I'm going to keep doing this until this number is 0. So this number I'm trying to get. So I'm going to check, is this bit available? No, it's not. Is this bit available? No, it's not. Is this bit available? No, it's not. Is this bit available? Yes, it is. Okay. Now I'm going to take the last bit of my current number, which is this, and then I'm going to set this bit to the same thing. So I'm going to do that, and then I'm going to shift this number so this is gone. Then I'll go to the next thing. Is this available? Yes. So I'm going to set this to this. So this will be 1. Then bit shift this to the right, get rid of it. Then move over here, set this to this, get rid of this. Go over here, so these are all available, set this to 1, get rid of this, and now we have 0. So you can do it in a bunch of ways, but this is one of them. But that's essentially the problem, is you just realize I can't change some bits, but I can change others. And let's take a look. That one. Yeah, so it's pretty short. So essentially, you just know that like if I'm building n numbers, the biggest one is going to be n minus 1, right? If I'm building 3 numbers, the biggest one is going to be the like number 2. Then I just check, as long as my n is non-zero, I just get the last bit, and then I check, is this bit available by anding 1 with this. So let's say like max is 4. Basically what this will do is this will move one I amount of time. So I also have an index. So like first I'll start here and I'll check like, okay, if this is a 0, if this ANDed together is a 0, that means this bit is off. That means this bit's available. So if this bit is available, then I will turn it to the same value as the last bit of n. And if it's not available, I'll just keep moving it. So that's why I said while this bit is on, keep going to the next one until you get the bit that's off. Then when you get to a bit that's off, turn it on to whatever the bit was in the number. And then keep moving the index up and keep shifting the number to the right. So you're essentially just basically filling in empty bits to the same bits of the number that you calculated. Hopefully that makes sense. Let me know if you have questions, but this is obviously going to be really good runtime because this is essentially, so to do I guess we could figure it out. So we only, we keep the same index on the number and we keep going. So this is basically going to be something like a log n plus log x runtime, which is like really, really good, right? So even though x is really big, it doesn't really matter. And space is over 1. Okay, so hopefully that makes sense. Yeah, I did solve this one pretty quickly because you just kind of recognize you want to start the smallest number possible. And if you've done, like, I don't know if I have like good intuition for it, but I realized what I need to do very, very quickly. This was kind of nice. Okay, so let's go to the next one. So this one's pretty difficult, but once you understand kind of what you need to do, it's not so bad. Also, yeah, the problem's a little weird, so let's take a look though. Okay. All right, so you're given an integer array nums, and the uniqueness is the sorted array that contains a number of distinct elements and all the subarrays of nums. This is a little weird. So basically, you go through every single subarray of nums. Let's actually make this probably a little bigger as well. So let's see, like this. All right, so you go through all the subarrays of nums, and you just return how many distinct elements are there. So the first subarrays of nums, and then you sort all those. So like this is a subarray, this is a subarray, this is a subarray, this is a subarray. So every one-length subarray will have one distinct element. So that's why you have 5 ones here. Now you check 2-length subarrays. So let's actually look at this one first. So here, every 1-length subarray will be one distinct element. So you have 3. Then every 2-length subarray, so this is 2 distinct elements. This is 2 distinct elements, so 2 and 2. And this is 3 distinct elements, so 3. In this one, so every one will be unique. That's going to be the case in everything. But now if you look at 2, so this is 2 distinct elements, 2 distinct elements, 2 distinct elements, 2 distinct elements. So you have 4 2s. Now you look at a subarrays of length 3. So this is only 2 distinct elements still. This is 2 distinct elements. So now you have 5 2s total. And then this is 3 distinct elements. So 5 2s and 1 3. Then when you have 4-length subarrays, this is 2 again. So 6 2s, I believe. Yeah, 1 2 3 4 5 6. Maybe I missed one, but actually you should have 7. But so this is 1, and this is 1. Oh yeah, this is the other one. So yeah, so that's the 7th one. So both of these, actually, so sorry, this should be length 3, right? So this is 3 distinct elements, and then the whole thing is 3 distinct elements as well. So it's like this is 3 distinct elements, this is 3 distinct elements, and this is 3 distinct elements. And yeah, there's 7 too. So essentially, you get all of those. So for every subarray, you just write down how many distinct elements do I have. You sort all those, and then the median is the middle. And if there are 2 middle values, so in this case, there's 2, 4, 6, 8, 10, 15. So you just pick the middle. So this would be the 8th one, which is here. But if you have an even number, you just use the left one. And they basically tell you, like, return the median of this thing. So in this situation, once again, you have 1, 1, 1, 1. Then for length 2, you have 2, 2, 2. So 3 2s. For length 3, you have 3, 3. So 2 3s. And then finally, this is 3 as well. So 3 3s. So same thing. So this is 4, 10. So you would pick the 5th one. So you'd pick this. So the key to this problem is instead of, like, you can't figure out for each array, like how many distinct elements are there for each subarray, because that's going to take too long. So I think that's going to be like n squared to get like every subarray, because you have to do like every start index and so on. So that's not going to work. But what you can do instead is figure out like, okay, how many subarrays do I have total? And you can calculate that. So the number of subarrays, if you think about it, in an array is, let me actually figure out how I calculated this before. Yeah, so you can start at every start index, and then you can end at like every index after that. And so it's basically, we can just like do the math really quick, but if you actually look, so the number of one link subarrays is 4 here. The number of two link subarrays is 3. This is how I did it actually. The number of the next one is 2, and then 1. So that's always going to be the case. So the number of subarrays for n is always going to be like 1 plus 2 plus 3 plus 4 plus 5 and so on up until n. So basically the sum of an arithmetic sequence of 1 to this kind of thing is the average times the length. So the length is n. The average is 1 plus n over 2. And so this is how many subarrays you have. So n times 1 plus n over 2. And this will always be a whole number, because either this will be even or this will be even, and then you just divide by 2. So for example, in this first one, this will be 3 plus 4 over 2. So you'll have 6 subarrays. So you can see there's 6 here. 6 here. In this one, it's going to be 5 plus 6 over 2. So it's going to be 30 over 2. So 15, which is 15. And then 4 plus 5 over 2. So 10. And basically the idea is once you figure out how many subarrays you have, so let's say I have like 10, I know that the median value will be at location 5, right? And if I had like 11, then it would be at location 6. So you figure out like median location, which is just the ceiling of n times n plus 1 over 2 over 2. So it's like the number of subarrays over 2, and then you do the ceiling. That way, if it's like 11, if you have 11 numbers and you want half, you would do 11 over 2, which would give you 6. And if you have 10 and you want half, it would be 5, the fifth one. Then instead of figuring out like how many distinct sequences do I have of each number, we can basically, the thing we can look for is how many distinct, or how many subarrays do we have with k or less distinct elements. So we can't quite figure out this for each one, but we can actually go through this and we could say like, okay, if we want 3 or less distinct elements, let's say for this, we can do that. Like that's a doable problem. And the way to do that, I can briefly go over it, I guess, is let's say we have like this 4, 3, 5, 4. And we're looking for 4 or less, or not. Let's not do 4 or less. Let's do like 2 or less. Let's see. Yeah, let's do 2 or less. So we should get 7. So this is just a easy sliding window, and you basically just keep track of, for every end element, what's like the start element that has to match. So in this case, we're looking for subarrays, number of subarrays, with at most 2 distinct elements. So here, basically we can just, like for the subarrays that end with 4, there's only 1, right? You start with 4, end with 4, so there's 1 there. Then if you end with this one, we only still have 2 elements. So the number of subarrays we have, like the valid window is this. So the number of subarrays that end here is actually just the length of the window, because everything in the window is going to be a valid subarray up until shrinking it to the first one. So like this is valid and this is valid. So we have 2 here. Now we have 3, so we have to shrink our window to this. And then we have 2 more, right? Because this is valid and this is valid. Then we have 3 again, so we have to shrink our window. So we have 2 more. So we have 7 subarrays with 2 or less elements. And if we actually look here, that is the case. So we don't quite know how many of each, but we know we have 7. And so if we know our median location, like if we know the median here is at location 5, we can basically just binary search how many elements we can have, and then the biggest number that gives you 5 or more is going to be your answer, right? So if the median is at location 5, the biggest number that actually gives you 5 or more, actually no, sorry, the smallest number, the smallest number that gives you 5 or more is like the one that just passes, and the one that just passes is going to be at the median location. So like we'd say, okay, so like we would basically try, in this case, we try all the number of distinct elements. So here you can just turn into a set. So we try like 1 through 3. 3 would pass, 2 would pass, and then 1 would, I think 1 would fail, right? So yeah, so for 1, like this is a subarray, this is a subarray, this is a subarray, and this is a subarray. The only way you can have multiple with 1 is if you had like 4, 4 or something. So basically here you would return 4. And so the smallest number that passes is 2. So that's why 2 is going to be the median. And that kind of makes sense because you know that, like, okay, I have 7 subarrays, so my median is here. And I have 7 subarrays that 2 passes with. So like I know for sure that this number is 2. Right? And so the smallest number that hits your median is going to be like your median. Because if this was 2 and this was like 1, let's say, then 1 would also pass. So that's kind of the idea. So we can do this for the other problems just to make it a little bit more clear. So let's try it. And maybe you can bring this up even to make it easier. So let's get rid of this and just try it for these. So same kind of thing. You draw out your array. So 1, 2, 3. And then you figure out like how many subarrays you have. So this is going to be 3 times 4 over 2. So you have 6. So you have 6 subarrays, which means the median's at location 3. So I need to try all different things, and then the smallest one that passes that gives you 3 or more will be your answer, because the median is over here. So the things we're going to try is 1, 2, and 3. So let's just say so those are the things that we can try, right? And the number of distinct elements, because it's never going to be more than that or less than 1, because like one element has 1 distinct element. It's never going to be more than 3, because you're never going to have more than 3, because that's all you have. So let's just say we try 2. So if we try 2, the number of subarrays with 2 distinct elements. So this is a subarray, so that's 1. This is still a valid window, so we have 2 subarrays here. And this is not a valid window, so we have to shrink. And we have 2 subarrays here. So this gives us 5 subarrays, which is greater than 3, so that's a valid answer. So 2 does work, but then we're going to try smaller than 2, right? So if 2 works, we don't care about 3, so we're going to try 1. So if we try 1, go back. So this is a subarray, so that's 1. This is a subarray, and this is a subarray. So we have 3 here. And 1 is the smallest number we got, so 1 has to be the median. And that's what it is. Let's finally do the last one. Okay, so let's just say, so 3, 4, 3, 4, 5. But that's kind of the idea, is you don't know exactly what's at the median, but you can just figure out like what passes, and then the smallest one that passes has to be your median. So here, we have 5 times 6 over 2, so we have 15 subarrays. So the median has to be at location 8, right? So we want things that pass with 8, and how many unique numbers are there? There's 3. So once again, we're going to try 1, 2, 3. And this is like our range that we have to binary search for. So let's try 2. So for 2, this is a subarray, so that's 1. These are both fine, so that's 2 more. This is still valid. We only have 2 elements, so that's 3 more. This is still valid, so we have 4 more. And now this is no longer valid because we have 3 unique elements, so we're gonna shrink, shrink, shrink. And then we have 2 here. So this is 12. So this works as well. Or I guess, sorry, not as well, but this 2 works for sure. So we know 2 works for sure, so then we can just toss the 3, and now we just have to try the 1. And if we try 1, so we get 1 here, then we move it. This is invalid, so another 1. Then we come over here, invalid again, another 1. Then we come over here, invalid again, so another 1, and another 1 over here. So we have 5, and we needed 8. So you know, like 1 is too short, basically. So we know that like one for sure isn't at this location, and 2 is the only one that gets past that location. So we know for sure that 2 has to be that. And yeah, the only way to have multiple subarrays of one distinct element is basically you just need to have multiple of the same elements. So for something like this, so you'd get a lot here, right? Like this would be valid, this would be valid, this would be valid, so you get like 15 or something here. But because it's not the case. So hopefully that makes sense. You can basically just like binary search for a valid number of distinct elements. And then the smallest one that passes is going to be your median. So let's take a look at that. Here it is. So the code is not so bad. Yeah, so the median is basically the number of subarrays, which is n times n plus 1 over 2, divided by 2, and then divided by 2 again. So if we have like, so the number of subarrays is n times n plus 1 over 2. And then the median of that is that over 2. So that's why it is the way it is. And then you just round it up. So if you get like 30, you would get 15. And then if you had an odd number, it would be at the middle, right? So if you had like 5, it would be at 3. And then you basically just make a function that gives you the subarray count. So this is the sliding window. So this is a pretty standard sliding window thing. And you just have a count of every element, you increase the count of every element, and then while the number of distinct elements is greater than the thing you're looking for, you shrink your window, and then the number of valid subarrays is just the length of the window. So you add that, you keep adding that to your result. And then your bounds are 1 and the number of distinct elements in the entire nums thing. So you can just turn it into a set and get the length there. And then just standard sliding window. So if it's valid, try things below it, and then here I didn't use a result, so right will be the valid number here. Yeah, so code pretty easy once you kind of get what you're doing. A lot easier than the contest before this one, so yeah. So this is going to be like, so essentially we're trying through every number of distinct elements, so I guess worst case scenario that's going to be like nums length, so we'll call this log n. And then for each one of those, we are iterating through nums. So it'll basically be m log n. Space. So we have a dictionary here. So I think this is just going to be of n space, because once again, if every single item is unique, that would be assuming, yeah, so every single item can be 10 to the 5th, and you can have 10 to the 5th items. So worst case scenario, you just have like 1 to 10 to the 5th or something, which would be of n space. Yeah, and that's going to be all for this one. And if you have any questions, as always, I think I talked about, yeah, like the time and space for the rest. I mean, I think the rest are pretty easy. Like this one is also pretty easy to figure out. So this is just going to be like n log n for the like length of the array, and then the rest of it is just you go through the array. So this number doesn't matter. Like this number could have been 10 to the 9th, it wouldn't matter. So it's that, and this is going to be 01, and then the first one was like basically 01 or something, or not 01, O of n time O of 1 space. So yeah, yeah, hopefully this was helpful, and if you have any questions, as always, you can write in the comments. I'll answer some stuff. So thanks for watching, and yeah, like and subscribe and stuff if you enjoyed this kind of stuff, and let me know what I can do to improve these. Thanks.